For example, if you have a heavy element and it backscatters more electrons, the more electron will illuminate the screen more. So you will see a bright feature there from where the electrons are backscattered more. I am giving you examples, right? This is just for example. Similarly, if less electrons are backscattered, the illumination will be less, right? That particle, that grain will appear a bit darker in comparison to the other. But if all the electrons are absorbed, then you will see a complete dark feature. And that will be a pore or a very huge dip inside the material, a crack inside the material, where all the electrons are absorbed and they are not coming back upwards. So all the information you get from the electrons is because of your detectors. That how many detectors do you have associated with your electron microscope. So never think that this microscope is allowing electron to cause only secondary electron microscopy and not the others. All the processes are happening, but if you have more money and can buy more accessories, then you can get more information. So information is for sale. You spend more, you will get more information. You spend less, you will get less information. All the features are there, but you don't have detectors to quantify and to know and transform them. In light microscopy, this is very important point, and this is the junction between the electron and the optical microscope, the light microscope. That in light microscopy, the numerical aperture of the lens and therefore resolution can be increased by number one, increasing the half angle, right? The half angle of illumination. B, increasing the refractive index of the lens by using crown glass, which are denser optically, and C, decreasing the wavelength of illumination. So it tells you these three things, right? And NA is basically the product of refractive index and the sign of the angle of illumination, right? So you have these options. Now, in light microscopy, the numerical aperture of a lens and therefore the resolution can be increased by, again I am repeating this, that the half angle of illumination, increasing the refractive index of the lens by using crown glass and decreasing the wavelength of the illuminating radiation. In electron microscopy, the refractive index cannot exceed 1. Think over it, right? Because you are playing with electrons in vacuum. It is complete vacuum. So in vacuum, you have no power over the index of refraction. It must be 1 and it is 1. Right? The half angle is very small and thus the only thing that can be adjusted is decreasing the wavelength of the illuminating radiation. So the refractive index cannot be changed and half angle is very small. The electron beam is coming from that wall clock height. So if the angle is a little bit wider, then they will go out of the microscope column. That is why you need very thin concentrated beam of electrons to reach your sample. It is coming from the half of that height. So if it is a little bit larger angle, then they are not of your use. They will hit the column of the microscope and they will not reach your sample. So the only option you have to play with is the wavelength of the illuminating radiation. Lambda is there. You know it from your FSC classes. You can change the lambda. There it is a long distance to complete one wavelength. But in that one wavelength, if you from here to here, so you cover several wavelengths when you decrease the wavelength, right? And the formula is lambda is equal to h over mv. V is the velocity, and this is the de Broglie's 1923 equation, which started the concept of wave particle duality. Ke is half mv square. Kinetic energy is half mv square, which is p square over 2mv. You know it from your FSC. Then p is equal to 2 mke under root from that equation. Then lambda is equal to h over p, which is equal to h over 2 mke under root. H over 2 MeV, Ke is in MeV in electron microscopy, right? So you have 2 MeV under root. H is Planck constant, M is mass of electron, and V is velocity of electron. And these are the values which are commonly used. Lambda is equal to H over, from those equations, H over 2 eV electron volts are potential, because you are accelerating the electron through electrostatic potential. Electron is a charged particle, and you have, just like the objective lens, the condenser lens, which limits and delimits, increases and decreases the radiation. You are dealing with photons in optical microscopy. They are not charged particles, but electrons are charged particles, and electrostatic potential can enhance or decrease their speed, right? So it is when you talk of lenses in electron microscope, they are not lenses as you think in the optical microscope. They are electromagnetic coils. You produce an electromagnetic field, and that field balances, focuses, accelerates the electron from the electron gun down to the sample, and then crosses the sample or deflected by the sample and reaches the screen. So lambda is h square over 2 EVM when I put the values there, right? And to 10 power 20. And when you put all these values, the wavelength turns out to be 150 over V under root. And that 150 over V under root is in angstrom. But this is your assignment. Put values there and calculate them, right? That how you relate the potential, the accelerating voltage of the machine to the electron wavelength. I said in the previous slide that the angle is so small that you can't play more with that. The refractive index of the vacuum is 1. You can't play with that. The only thing which you can play with is the wavelength of the electron beam. And the wavelength of electron beam is solely dependent upon the V. Right? Substituting 200 electron volts per V gives lambda is equal to 0.87 angstrom. For a beam of 100 kV, we get a wavelength of this much. Right? Think over it. I'm saying that for 200 kV gives a lambda of 0.87 angstrom. But for 100 kV, I am getting this much. But this is theoretical. Right? If theoretically I go, I will get this. But when I go through the potential, which accelerates the electron, then it gives me that, practically. And a theoretical resolution of 0.01 angstrom should come when I divide the 0.389 by 2, 0.0389 by 2, it will give me 0.0195. But it is not the case. It is theoretical. But in actuality, most EMs will only have an actual resolution of 2.4 angstrom at 100 kV. Right? If you have a 100 kV electron microscope, we are saying it has 2.4 angstrom resolution. But that also depends upon the quality of the user. That how much expert the user is, how much focusing is allowed in the machine. If the machine is old, there are many features which cannot be used there. The errors will be more. Right? So the quality of the operator as well as the quality of machine determines the actual 2.4 angstrom resolution. Nowadays, most of the machines in the labs are 200 kV and above. The 200 kV and above means the shorter wavelengths. The shorter wavelengths means that you can use thicker samples. When the wavelength is shorter, the transmittancy will be more. The energy in the beam will be more. The shorter the wavelength, the energy is higher. The more energetic the beam is, its transmittance will be more. So, you will take sample to the machine, but which is, for example, 30 nanometer thick. The 100 kV electron beam will not be able to transmit through that. But if you use 200 or 300, and there are now up to MEVs, electron microscopes, where you can study a little bit thicker sample as well. There are certain samples which cannot be thin beyond a certain level. And for those samples, you must have a high voltage, high acceleration voltage electron microscope. Okay, so these were the two persons, Ernst Ruska and Max Nall, who developed the first transmission electron microscope in 1932. And this is the first electron microscope, the first on the continent, was built at the University of Toronto, Canada, and was successfully operating in 1939. So look, the total age of microscope is not more than 60 years. And the actual engineering of material started with the invention, with the development of the first transmission electron microscope. I told you in the previous lectures that most of the knowledge prior to the invention of transmission electron microscope was empirical. right? It was totally empirical. People couldn't see the interplanar spacings. People couldn't see the crystals, dimensions. People couldn't see what they substituted at specific positions in the unit cells. But when you put this thing in this will happen. This was the whole game of materials. Right? When you put this thing in this will happen. If you put salt and water, they will become saltish. Why will they become saltish? That was not known. And why is the science? Why is the science? And putting something in something and getting something, it was empirical knowledge. So no science was there regarding the material. Material were there, but science was not there. And the birth of material science actually started from here. Chinese developed porcelain, which is called fine china, about more than 1300 years ago. And for 1000 years, the Europeans tried their best, but they couldn't copy them. And the porcelain used to be called the white gold in those days. And it was about 1970, 19, I don't remember exactly now, but about 1900 something like that, that some Italian and Germans started to make porcelain. They could make pots from clay, but they were not white, just like your own people used to make in this land, right? They could make it. They could make pots for cooking foods, for bringing water, but they were not white. And that skill was known to the Chinese only. And they kept it secret for 1000 years. And this bone china is a pure English product. So by all these stories, I mean that the material were in use. People used materials. Bronze was in use, iron was in use, stones were in use, and when people excelled in making tools from stones, that excellence in stones made that age stone age.